Alrighty folks, we're moving right along, and this week we're going to take a look at Chapter 7. And Chapter 7 is going to teach us something that's really fundamental in statistics and data analysis, and really just adding to our toolkit of what we can do in Excel with some basic statistical tools. And this concept of sampling is hugely important. It's used in almost all research, and having a good working knowledge of sampling and how to use Excel to take samples and then how to do inferences based on those samples is just hugely important. So we're going to cover it at a pretty basic level, and as I've said before, I think it's most beneficial for us just to really get some data and practice these concepts rather than talk about them in theory. So I'm going to just briefly go over some terms and concepts here, and then we'll jump right into Excel with some examples and practice problems to get a hands-on feel for these concepts and how they're used. Okay, but first let's talk about what sampling is and some concepts and terms we need to know before we really get into doing it. Right, the goal is to infer, and it's really an educated guess, something about a population without measuring every item in the population. So we want to know something about, say, our customer base, or the responses of potential customers to a certain product, but there's no way we could possibly contact all possible customers, or even all current customers. For a large company, you've got maybe thousands, millions of customers. There's no way you can contact them all to find out their feelings about a product or something along those lines. So what we're going to do is just take a small subgroup and make an inference about the overall group based on the findings we get from the subgroup, and the subgroup is the sample. Okay, you're probably familiar with this, I hope, from just your basic background knowledge of statistics and survey measurement and that kind of thing. Hopefully you're familiar with these terms. The population, which we designate, notice the capital N. So when we use capital N, we're talking about the population. Now, members could be people, or it could be any kind of variable, any data we're interested in. It could be the number of defective parts. It could be the number of parts. It could be the number of orders. It could be the dollars that we earned or something like that. So we could say, think members or items. They're not necessarily people. And that's the whole thing. We're making an inference about consumer preferences for all consumers in the U.S., or all male consumers in the U.S., or all baby boomer consumers in the U.S. Okay, any of those groups is going to contain millions of people, and of course we cannot contact them all. So we'll take a subgroup, which is a small n, of maybe 100 or a few thousand, and survey them or observe them, and then make inferences about the overall population based on the results of that sample. The frame is just the term for the list of the members of the population. Sometimes we have this with smaller populations, and we'll work problems where we have a listing of all of the orders from a company, or a listing of all the previous customers from a company, and that could be a substantial list. You could have tens of thousands of entries there, and we really don't have the time or energy. Even though we could theoretically find the population parameters, it's much easier to sample it and find really good estimates of the population parameters. Okay, and we don't have necessarily a frame for really large populations like the United States population, or all baby boomer, or something like that. It's not relevant, because what we're going to learn here is that the sample is going to be good enough most of the time. Okay, of course the sample, which again designated with the lowercase n, that's just the subgroup that we draw to use to make our inference about whatever we're trying to measure. There's different kinds of samples that we could get. There could be probability samples or judgmental samples. We're really only interested in a probability sample, and that's where the members are chosen randomly. If we choose the members of the sample randomly, then we can use the laws of probability. If we choose them based at the researcher's discretion, basically whatever's convenient, whatever's low cost, well, that's called a judgmental sample, and it's not going to be usable in making inferences about a population, because the laws of probability won't be applicable there, and things like our normal distribution. So we're only interested in probability samples. We'll create probability samples using random numbers, using Excel tools that we're already familiar with, and we'll just say forget about judgmental samples. Okay, so let's talk about sampling methods. How do we go about acquiring a sample out of a population? And there's 4 things that the book talks about, and we'll spend almost all of our energy on the first one, which is a simple random sample. The way a simple random sample works, the definition is that every possible sample of size n has some probability of being chosen. So to make things really simple, And we'll actually work through a little bit more detailed version of this to learn something about what kind of how we can make really good estimates of the population from the sample. Let me just run you through a quick example where we only have 5 people in our population. I'll give them names: Alice, Bob, Charles, Deb, and Edgar. So we have people A through E, and that's our total population. And we're going to choose a sample, so that's n equals 5. We're going to choose a sample of n, lowercase n, equals 2. Well, what are the possible samples we could get? Well, we could get Alice and Bob, Alice and Charles, Alice and Deb, Alice and Edgar. We can denote that like this. Okay, we could get Bob and Charles, Bob and Deb, Bob and Edgar. We've already got Alice and Bob. We could get Charles and Deb, or Charles and Edgar. We've already got Charles and Bob and Charles and Alice up here. And then finally we can get Deb and Edgar. We've already got Deb and Charles here, Deb and Bob here, Deb and Alice here. Okay, so I've made a list of all the possible samples of size 2 up here, and as you can see with a simple count, I've got 10 possible samples. Now the definition of a simple random sample is that each sample has an equal chance of being chosen, right? So if I could randomly draw one of these samples, I got an equal chance of selecting any of them, and that chance would be 1 in 10. So we could say it like this: probability equals 1 in 10 for drawing any of those samples. And we could also say that any individual has an equal chance of being drawn in any sample. So if you look at the samples, you see that Alice is in 1, 2, 3, 4 of them. Or let's look at Deb. She's in 1, 2, 3, 4 of them. Edgar's in 1, 2, 3, 4 of them. Each individual is in 4 of the 10 samples. So each individual, so the probability of a sample is 1 in 10. The probability of getting an individual, because individuals are in multiple samples, is 4 in 10, or 40%. So I've got an equal probability of drawing any sample and an equal probability of drawing any individual. And that's what we mean by simple random sample. Okay, so let's practice making samples, simple random samples, and I've got problem 7.1 up here in the spreadsheet on page 314. And this is our old employee data set for Beta Technologies. We actually used this a while ago. But this time it says, for this problem, consider this data set as the population frame. And then in A, using the method in this section, generate a simple random sample of size 20 from this population. Okay, and you'll notice we have 204 entries, so that's 203 members, so we're taking about 1/10 of them here in our sample. How are we going to do this? What we want to do basically is use a random number generator, which we're hopefully very familiar with, to assign a random number to each employee. And then we'll just use some kind of arbitrary criterion of those random numbers. We'll take the top 20 or the bottom 20. That we could take the middle 20. Anything that's kind of arbitrary, because they're random numbers, will also be a random draw. So what I'm going to do is insert another column over here and just type in. I'm just going to type in random number, and that's going to be equal rand, open close parentheses, and then double click here to fill it down. Okay, now remember, the thing about random numbers is because they're a function, every time we recalculate anything, we recalculate all those random numbers. So the trick here is to do what the book calls freezing the random numbers. So I've got my random numbers here. I'm going to create another blank cell here, and notice it recalculated them. That's okay, it can recalculate them, but what I've got to do is freeze them. So I'm going to select, I'm hitting Control Shift down, all the random numbers. I'm going to copy them, Control C. Then I'm going to click here on B and paste the values. So now I've got frozen random numbers. I'm not recalculating them every time. The problem, if I recalculate them every time, is that I can't fix my my draw of my sample. So I've got my random numbers fixed, and I actually could go ahead and delete that, but I'll go ahead and leave that there. So, and notice every time I press Enter or recalculate anything, you can press F2. Those random numbers over there regenerate, but these ones stay the same. Okay, so now all I want to do is sort on the random numbers. Okay, so I want to sort the random numbers, so I'm just going to go up to Data. Actually, I'm going to select B. I'm going to sort them A to Z. I'll let it expand the selection for me. Okay, now you'll notice I have the smaller random numbers down here. I just want to take the bottom 20 of them, so that will be 2 through 21, and I'm going to let me copy those with the column headers. Control C, and I'll go ahead and paste those over here in K1, and I'll just paste them as values again. just in case I had any formulas, and I'm going to auto adjust the columns. Okay, so there's my random sample. Okay, so that's part A. Pretty straightforward, I think, pretty easy. Let's move on to part B. Part B says use stat tools to generate 10 simple random samples of size 20 from this population. Well, we don't have the stat tools add-in, but it's not going to be too hard for us to redo our procedure based on the random numbers. So we're going to do this 10 more times by going back over here. Okay, my random numbers have recalculated, and I'm going to again copy those and then paste their values, and again sort A to Z on the random numbers. And now I've got my second random sample. I'm going to copy that over, and I'll leave a space here, and I'm going to leave 2 spaces. I'm going to paste this again. So there's sample number 2. Actually, let's make a column up here. Let's call this sample, and we'll call this sample 1, sample 2, 3. So we'll just keep doing this 10 times. And of course, because you have your own random numbers and I have my random numbers, we'll have different samples. That's okay. We'll have slightly different results. That's okay. Let's just go ahead and do this 10 times, and then we'll come back and talk and move on to the next step. Okay, so I'm making my final random sample. I'll go over this procedure one more time. I'm selecting all my random numbers, Control Shift down, copying them, Control C, going back up here, and then I'm right clicking and just pasting values. Then I'm going to select B through I, and I'm going to sort on the random number, smallest to largest. And then I'll pick the 20 entries for my data set, copy them, Control C, and then scroll down, and you can see I've done 9 of these, so I'll do one more here, Control V, label that sample 10. Okay, so there are my 10 randomly drawn samples using random numbers from my data set. And now we're ready for part C, which just says calculate the population mean, median, and standard deviation of annual salary. So I don't have to scroll down. Let's just do this up here by inserting a couple columns. I'm going to just label the salary stats. I can get rid of my random numbers now. Actually, I can get rid of all of them. You can leave them if you want. I like to keep things tidy. I don't like to see those numbers change every time. So we want to find the mean, median, and standard deviation of salary, which of course we have the population, we have all the items, so we can do that here, and that's entries G2 through 205. So I'll just run those, average G2, G205, median G2 to 205, and standard dev. Now this is a population, we've been told that, so we're going to use standard dev .p G2 through G205. Those are dollars, so other than standard deviation actually, so I'm going to format them as these two. I'm going to format as currency with no decimal, and standard deviation, we'll just leave that as a number with no decimal. Okay, so the mean is 71,000, a pretty wide spread of 30,000. Standard deviation, median 68,400. Okay, those are the population parameters. We can label that up here, salary stats, population. Okay, so those are population parameters. Let's maybe highlight them so it's easy to refer back to them. And it asks us to calculate the sample mean, standard deviation, salary for each of the samples in parts A and B. Let's do that in column J here, and the mean is going to be just the average of these 20. Likewise the median, just the average of these 20. And standard deviation, and now it's a sample. So we use the sample formula. We're just dividing by n-1 here instead of n. And again, format them. Okay, so I've got my sample, and let me highlight these in a different color just so we can easily reference and compare. And we can see that the sample mean isn't very close. The median is pretty close, and the standard deviation is quite a bit larger. But what we're getting at here is if we sample enough times, we've got a distribution of samples, and the mean and standard deviation of that distribution of samples is actually going to get very close to our population mean and standard deviation. And in fact, the more samples we do, the closer and closer we get, and with a sufficiently large number of samples, we're going to actually get right on the dot of the population parameters with our distribution of sample parameters. That's we're going to work up to that here in a minute. But let's go ahead and just copy these formulas. And if I just move them down 20, because I didn't lock any of my cell references here, it'll shift the reference cells down 20. So I'm going to just copy that block, and each spot where I numbered my sample, I'm going to copy it in. And what we're going to find is that more often than not, our sample mean standard deviation is going to be pretty close to the population values. Occasionally they'll be off, they'll be quite a bit off, but they're typically going to be pretty close. Okay, so I've actually only done this 9 times because I've realized I screwed up on one of my random samples, and I'm not going to take the time to redraw it, but I have 9, good enough. And let's see what we got: 76,000, 70,000, 65. Now here's one that's pretty far off, below the true mean of 71,000. Actually, that's not far off. My true mean is 71,000. My samples are 76. That's about 76, 74, 64. That one's pretty low. That one's about 80. That one's pretty high. 78, a little high. 65. Okay, so I'm consistently within, we'll say 76 there. I'm consistently within 5,000-6,000. It's actually not too bad. Same thing for my median. That one's almost right on. That one's pretty high. That one's pretty little high. That one's pretty close. That one's pretty close, a little bit on the low side. That one's a little bit on the high side. That one's really low. Okay, occasionally we're going to get a sample that's way off, but you can see we typically get a sample that's pretty close. So we've got an idea that with any given sample, we're within a certain range of the actual population value for any of these, for whatever we're looking at, whether it's mean, median, standard deviation, whatever parameter we're interested in. That's kind of step 1 in how we're applying this idea of sampling and using the sample parameters to estimate the population parameters. We'll come back to this concept here in a bit, but let's continue with practicing. Okay, so we're looking at problem 7.2, and it says this file contains data on the 1,995 students who have gone through the MBA program at State University. You can consider this the population of State University's MBA students. In the first half, it's going to just ask us to find some summary data. So it wants a mean standard deviation for each of the numerical variables in this population, and then the proportions of students who are male, international, under 30 years age, and those with an engineering undergrad. So all of that stuff I've done for you, and I'm not going to go through very much detail how I did it, but I'll show you the formulas. Simply took the averages of all the entries in the age column, so that's B2 to B1996. Okay, average in the children column, average in the GMAT, previous salary, monthly expenses, school debt. So that's pretty easy. Okay, then likewise the standard deviations. And notice I'm using the standard deviation.p because the book told us this is the population of students. Okay, so there's my summary data, pretty easy. As for the proportions, I put in the count here. I have 1,995 just so I could calculate these a little easier with cell reference. And then for percent male, I just used a simple COUNTIF formula. So I counted in the range male, and I divided that by my total count. I could call this the total count, maybe a little more accurately. So percent male, okay, I counted the male, divided them by the total count. Percent international, now there's lots of different countries or regions there. So I could count India, Europe, other, South America separately. Or I could just count US and subtract that from the total, which is exactly what I did. So I've got 1995 minus COUNTIF, the range US, and then divide that by the total count. Okay. And likewise under 30, you can use greater than, less than operators in the COUNTIF criterion. So I counted if that range, quote, less than 30, end quote, divided that by the total. And finally with engineering major, that's a simple COUNTIF. Okay, so I just use COUNTIFs to get all this data. Pretty straightforward. If you're wondering, well, why are we collecting this data? The reason is because we're going to be taking a random sample here in a minute. We want to compare our random samples to these population parameters. We want to compare the same parameters in the random samples to see if they're close, see how close they are. Okay, so next, step B, using the method in this section, generate a simple random sample of 100 students from this population and find the mean and standard deviation of each numerical value in this sample. All right, so what does that mean? Well, that means I'm going to add a column of random numbers equals rand, open, close parentheses, fill it all the way down. Then the next step is to copy all my random numbers, Control C. Let me scoot back up here and paste them here as values, remember, to freeze them. And now I'm going to select this whole thing and sort on my column M, which is my locked random values. Okay, so I've sorted by them. And I'll just take my first 100. I'm going to take the labels as well. I'm going to go down to 102. 101 rather. I'm going to go down to 101. Okay, I'm going to select that whole range. That's my sample per the random number process. Control C. And let's go on over here to the right and paste that in here. Okay. So there's my random sample. I'm actually going to paste this down a couple rows so I can put my summary stats up at the top so I don't have to scroll up and down to compare them. So it wants me to find the mean and standard deviation of each numerical variable in the sample. Okay, easy. Let's just do this. Mean, standard deviation of each numerical variable. So that'll start, let me move these over. That starts with age, and I'm just going to average this range. It's down to 103, and standard deviation. Now this is a sample, so standdev.s, same range, T4, T103. And then to find all the other ones, I can just fill this over. And of course, some of these things aren't numerical, so they're not going to compute. I'll just delete them. And now I've got the mean and standard deviations. I've got my means and standard deviations for my first sample. Okay, and then the question says, is there any way to know without the information in Part A whether your summary measures for the sample are lower or higher than the supposedly unknown population summary measures? And of course the answer there is no. We don't really know. Now what we will learn here through the central limit theorem pretty soon is that we can be pretty confident that they're within a certain range of the actual population values, but we don't know whether they're high or low without having the population parameters here. Okay, but let's just compare them. So our mean age in our sample 31.9, that's a little lower than the actual population mean over here, 32.3. The standard deviation's a little bit lower than the population. Mean number of children 0.22, that's also a little bit lower. I think that's pretty close though. Standard deviation's pretty close too, 0.5 versus 0.55. GMAT score, our sample is 702.5, our actual 703, that's almost right on with the standard deviation 41.1, almost spot on to the 41.2 in the population. Previous salary, we're undershooting that a little bit as well. Looks like everything in this sample is going to undershoot, and the standard deviation's undershooting a little bit. Monthly expenses, 1846. That's overshooting a little bit, just a little bit though. I think that's pretty close. Standard deviation 411 versus 425, and then school debt 27,031 versus 27,312. Again, pretty close. So I'm liking my sample. I'm pretty. I see that sometimes it overshoots a little, sometimes it undershoots, but kind of on average is capturing the population parameters. Okay, so part C says use stat tools to generate 10 simple random samples of size 100. Well, we don't have stat tools, so we're going to have to do this the manual way, just like we did in the previous problem, but that's okay. It's good for you. So we'll generate 9 more. We've already done one. And then we'll say for each, find the mean of school debt and its deviation from the population mean. And basically what we're going to do here is say if we take a bunch of samples and kind of average out the summary statistics on them, are we getting close to the population parameter on average? Okay, and if that didn't make any sense, you'll see what I mean here in just a minute. But first off, I'm going to clean things up a little bit so this doesn't become unwieldy. I don't need the student IDs. I'm going to go ahead and just get rid of them. I do need age, gender, nationality. I need all the things that we did the proportions or the averages on previously. Let me shrink some of these down a little bit though so we can economize on space. Okay, so I just shrunk that down a little bit, and here are my random numbers Just leave that as is. Okay, so I think my random numbers have recalculated, so remember the procedure here. Select them all, copy, paste in the values here, select only the range I want to sort on, and then I'm going to sort by the frozen randoms, smallest to largest. Okay, then I'm going to grab the resorted data set, and I'm going to only grab the first 100, which would be down to row 101. I'm going to grab the first 100, my original data set, which is down to, whoops, way too far, down to 101. I'm going to copy just those, and then go ahead and stick those over here. And this is sample 2. And we'll do this again 8 more times. And once we've done that, then we'll take the summaries and then compare it to our original population parameters. Okay, so hours later, well, it didn't take that long, but it was a little tedious. I have made my 10 samples, and as you can see, I labeled them in the age header, S2, S3, 4, 5, 6, and on to 10. Okay, so I've got 10 nice random samples here. And for that student debt column, I took the average in the very top row here. And just for convenience, I moved all those averages over here. So I've got the mean of student debt for each of my samples. I made myself a new little table here. Now I want to calculate the deviation from the population mean. And it says it wants me to have a negative number if it's below the population mean. So, okay, now to do that, I'm going to take this is going to be a formula where I take my sample mean and then subtract from that the population mean, which we calculated in A. I'm going to lock the population mean in so we can drag the formula down. So my first sample was 280 less. My second one's 148 less. My third is 414 less. Let's just fill it all the way. Okay, here's 741 greater. Here's 129 less. Here's 4,000 greater, 1,000 greater, 2,000, 3,000 less, 1,000 greater. Okay, so sometimes it misses low, sometimes it misses high. Usually it's pretty close. Occasionally here, that's pretty far off, but $200, $100 when we're talking 27,000, that's pretty close. So there's only a couple here that I'd say are way off, and the rest of them are fairly close. But that's not all we want to do. It says what is the average of these 10 deviations. So let's format this. Let's average those deviations, and it's 305. Okay. Says, what would you expect it to be? Well, ideally it would be 0, pretty close to 0. I would say this is close enough to 0, given that we've got a magnitude of $27,000, and our average deviation from each sample compared to that is only $300. So I think we're doing pretty well. Okay, finally part D, which says we want random samples to be representative of the population in terms of various demographics. For each of the samples in part C, find each of the proportions requested in part A. And what I did was at the top of my 10 random samples, I just extended these calculations that we had already done, copied them and pasted them for each sample. And I cut out the column for number of kids because we're not interested in that. We're just interested in these 4 proportions here. Percent male, percent international, under 30 in engineering. So I got those proportions. I used the same kind of count if formulas I used over here to calculate them for the population. Divided them all by 100. My sample sizes in each of my random samples are 100. And then, just for convenience and comparing, I've copied them down into this table here. So I've highlighted the values which I've copied down, which we calculated in A for the population. And then we can see for sample 1, 2, 3, 4 through 10, we can compare those percentages. So let's look at them. For percent male, okay, the actual population, remember, is 59.9% male. Well, sample 1 says 64%. That's a little high. Sample 2 says 49. That's quite low. Sample 3, 63, touch high. Sample 4, 57, touch low. 56, touch low. Touch high, a little bit high. Just a touch high, a little bit low. Just a touch high. So as you can see again, so sometimes we miss a little bit high, sometimes we miss a little bit low, but on average, we're capturing it pretty well. And actually, let me do this. Let's average out the samples again, even though the book's not telling us to do this. I'm kind of curious, and see how close we get. So average of these. And if we average the samples, and this is actually an important point that we'll need going into the next problem and one of the main concepts in this chapter, the central limit theorem. See, if we average the samples, we actually get pretty close. Okay. Again, with international, sometimes we miss a little low, and occasionally we're a bit off, but mostly we're pretty close, either but on the low side, but on the high side. Okay, sometimes we're a little bit more off, but on average we're getting pretty close. Okay, same with under 30. The average of averages is almost spot on, even though some of them are substantially off. 16 is pretty far off on the low side, 30 is pretty far off on the high side, but we've got a pretty good chance of getting a measurement of this that's close to the population, the true population value. Okay. One final thing we could do to think about how far off they are, or just a way to visualize it, would be to take these values and let's do this, and chart them as a column chart. And we could draw a line in here. Let's just draw a line at the population value. So I've drawn a line at the population value, as you can see, again, sometimes a little high, sometimes a little low, and occasionally we're way off. Here we're way low. But we're kind of bracketing the population parameter with taking a bunch of samples. Okay, so the point of this whole exercise is really just to get us to accept the idea that when we sample, we got a pretty good chance of getting close to the population parameter, especially when we have a larger sample size. Okay, so that's the knowledge we're going to build on going into the next few problems in Chapter 7 here, and then we'll take that a little bit farther into Chapter 8 and 9, and we'll really then have a toolkit that we can use to do some full-blown statistical inference. So now we have a very thorough understanding of sampling and how to do it in Excel, which is even better. So now we want to move on and say, well, what can we do with this? And what can a sample tell us about the population now that we know how to draw a sample? Well, we've actually kind of already seen in that tedious exercise we just worked on that the sample parameters, such as the sample mean, are going to more times than not be pretty close to the population mean. So we have a sense that the sample is going to be a good estimator of the population mean. So we'll wrap up this discussion by saying, how good of an estimator of the population mean can the sample mean actually be? So this is our main concept here, the idea that with a good random sample, there's a really good chance the sample parameter is roughly equal to the population parameter of interest, such as the population. The difference is known as sampling error. That's the difference in what we call x bar, the x with a little line over it. That's the sample mean, and mu, the population mean, just based on what I like to call luck of the draw or randomness. Okay, just because there's a lot of possibilities that we could get from our sample and a lot of possible means. They are going to be clustered around a certain value, but we could, by chance, get an extremely low or extremely high sample mean. So then in that case, we'd have a larger sampling error. Okay, but more often than not, our sampling error is going to be confined because the sample means are going to be clustered around the population mean, as we've seen when we constructed the samples. And that's really why it's so important, even though it was really tedious for us to make all those samples like we did in 7.2. It was important for us to see that with our own eyes, so to speak. Okay, now you could have error other than sampling error. You could have a difference in x bar and mu due to other factors other than your randomness of your sampling. And that would be if you don't have a good sample. So that could be things like non-response to surveys, if you're collecting surveys of a sample of a population, non-truthful responses to the survey, measurement error, just making mistakes, voluntary response bias. People will tend to not maybe be truthful, especially in certain kinds of questions that are really sensitive information and what have you. Okay? And we're really not interested in any of that. We want to be aware of it, but we're going to go with an assumption that we've got a good random sample, and so that any errors we have is sampling error and not non-sampling error. And the good news is about the sampling error is that because it's going to be subject to kind of the probabilities of the sampling distribution, we can handle it probabilistically and we can work with it. Okay, so we're getting pretty close to where we can say something substantial about kind of exactly how close our sample mean is going to be to the population mean, but there's a few more concepts we need to lock down first before we move on. And really, as I've mentioned, we'll really just kind of focus on practicing with this concept in Excel so it really sinks in. Because when we work with it in Excel and see it in practice, I think it makes it a lot easier to understand. But let's cover a couple more terms here, and then we'll be ready to jump back into Excel. Okay, point estimate, and that's our x bar if we're looking for the sample mean, if we're looking to estimate the mean. That's what I'll call a best guess of the population parameter based on the sample data. Okay, so we're estimating, and we call it a point estimate. That's just kind of some jargon. Okay. The sampling distribution, however, of that estimate is important. And the idea is here that we could draw a whole bunch of different random samples and get a whole bunch of different estimates. Those samples themselves are distributed in a certain way that's going to be useful for us. In fact, they're distributed normally. And so we're going to be able to kind of apply all the statistical toolkit that we've been building up until now. Okay, so we've got this idea of a sampling distribution. This is all the possible samples of a particular sample size that we could potentially randomly draw from a population. And that sampling distribution is going to have very unique features that are extremely important for us moving forward. Okay. The confidence interval is a range surrounding the point estimate plus or minus a certain distance. And we calculate that from the sample data, and we'll be able to eventually say that we can construct a confidence interval with a given size. We could say we're 90% confident that the population parameter lies within these bounds, or 95% confident, or 99% confident. You'll see exactly how that works here in a moment as well. Okay, the idea of an unbiased estimator, a point estimate with the mean x bar equal to the true population parameter mu. So what we'll also discover is that with proper sampling technique, and specifically with proper sample size, our expected value of the point estimate is going to approach the value of the population parameter. So we're going to get to the point where we can say what we need to do to get a very good estimate of our population mean or whatever. Okay, then finally, the idea of the standard error of the estimator. And this is simply the standard deviation of that sampling distribution that we just talked about. The sampling distribution is the distribution of all the possible estimates of the mean, for instance, that we could draw from any possible sample. Well, that's got its own distribution, and any distribution is going to have its own mean, standard deviation, what have you. How do we calculate that? It's kind of like calculating a sigma, which is the square root of the variance, but here we're going to actually take the sigma of the population, the standard deviation of the population, divided by the square root of the sample size. Now, if we don't have the standard deviation of the population, which we probably wouldn't be likely to have if we're estimating stuff, how in the heck would we know the standard deviation of the population, right? If we knew that, we'd know the population mean. So we're typically not going to have that. That's okay. We're going to just fill in and estimate the standard error of the estimate with the sample standard deviation denoted by s here. So we'll take s over the square root of n, and that is going to be equal to, approximately equal to, the standard error of the estimate. But this brings us to the idea of a confidence interval. And this is a really important concept that we'll be using quite a bit here in this unit, and you'll probably be running into lots of applications with, especially if you're working with a lot of data. Now, we're working up to this idea that the sampling distribution is itself a normal distribution, and I'm going to show that to you in Excel. It's much easier for me to show it to you than to really talk about it. But if you can run with that for a minute, with a normal distribution, kind of the main feature of that is, by the empirical rules, we've got so much of the probability within a certain range of the mean, and we know that 95% of observations, for example, lie within 2 standard deviations on either side of the mean. Okay, well, if we're talking about estimating a sample for which the distribution is normal, for any sample mean we get, we can therefore say that, well, we're pretty 95% certain that the true mean, the population mean, is within 2 sample standard deviations to either side of it. Okay, and this is going to be the formula we use. X bar, which is the sample mean, plus or minus 2 times s over square root of n. And we'll work some example problems here so you see how that works here in just a second. Okay, now finally the main idea really of this whole chapter and this whole unit, the central limit theorem, and this is what we're really going to look at in Excel, but let me give you the formal definition first. And this is straight out of the book. It says, for any population distribution with mean mu and standard deviation sigma, the sampling distribution of the sample mean x bar is approximately normal with mean mu and standard deviation sigma over square root of n. And the approximation improves as n increases, and we'll see that very vividly in an Excel simulation in just a minute. Okay, but what does that mean? It basically means a large enough sample will give us really good estimates of the population parameters. So if you don't understand the logic of this, that's okay. I know I'm probably not very good at explaining it. It's really tricky. But just you can run with this, and I'll show you how to do things in Excel as long as you kind of know this fact or just accept this idea. Large enough sample will give us really good estimates of the population parameters. This example from the textbook, 7.5, and let me just read what this example is doing for us, and I'll show you. It's really neat what it shows us. This is a wheel of fortune type thing where you spin a wheel and win a prize, and we're going to calculate the average prize that you would win with 1 spin, 2 spins, etc. So it says, suppose you have the opportunity to play a game with a wheel of fortune similar to the one on TV. When you spin a large wheel, it is equally likely to stop in any position. Depending on where it stops, you win anywhere from $0 to $1,000. Let's suppose your winnings are actually based not on 1 spin, but on the average of n spins of the wheel. For example, n equals 2, so you spin it twice. Your winnings are based on the average of 2 spins. And then it says, how does the distribution of your winnings depend on n? Okay, so we're going to run a simulation here, and this is exactly what we're doing in this field. Okay, so what this formula is doing, it's basically making a random number and then multiplying it by this value up here, 1,000. It's a little more complex than that, but that's essentially what it's doing. So, and remember the Excel random numbers between 0 and 1. So, it could be at max, well, at minimum it could be 0, and the winnings is 0. Or at max it could be 1, and then the winnings is 1,000. And you'll see here we've got 1,000 iterations of this, and sometimes it's really close to 1,000, and sometimes it's close to 0, but it's uniformly distributed in between there. Okay, and then what we're going to do to calculate the winnings over here is average out the winnings based on any number of spins. Of course, if we're only spinning once, and the other thing this formula does is only puts a value down if the spins here is the number of spins we've indicated up here. And we'll change this. We'll enter 2, and you'll see now it'll populate the values for 2 spins, and then we're going to take the average winnings over here based on however many spins we specify right here. Okay, but let's keep it with 1 spin, and of course the average, the winnings, the average is the amount of the first spin because we're only averaging one thing. What we want to look at is right in here the mean and standard deviation, and you'll notice that the mean is going to stick pretty close to 500. It'll move up and down a little bit from that. The standard deviation will move a little bit up and down from that. And then the histogram, which let me pull it up here so we can see it as we populate this. Okay, and you'll notice for only 1 spin, the histogram is pretty flat. It's a pretty uniform distribution of possible results. What that tells us is that any outcome basically between $100 and $900 is equally likely. That's if we're only spinning once, and that of course makes perfect sense because we're basically just multiplying that random number times 1,000. Okay, but here's the neat thing. As we increase the number of spins, so now we're the winnings is now an average of multiple spins. Notice what happens to the histogram. Now the winnings are far more clustered around 500, and note that the mean is still 500 or very close to that. It varies a little bit because of the randomness. And the tails start dropping off. So the odds of winning, the probability of winning a really large prize around 900 or a small prize around only 100 starts to really diminish because we're now averaging out 2 spins. Watch what happens when we increase that to 3. Okay, it's even more pronounced. The tails really fall off. The mean stays around 500 though. The standard deviation falls a little bit because we're clustering around the middle. Okay, let's go to 4 spins. Let's go to 5 spins, 6 spins, 7, 8, 9, 10. Okay, look familiar? And I'm going to just calculate again. There we go, I like that. What does that look like? Well, that looks like a normal distribution, doesn't it? And that's because it is a normal distribution. What's going on here is basically a sampling distribution of not a sample mean per se, but of this calculated winnings amount, but that's kind of like a mean because it's the average. You'll see in the formula there, it's the average of these 10 observations. Okay, so this is showing us exactly what's going on when we take a sample of a population and calculate its mean, and we know that its mean is going to be distributed normally. Even if, and that applies even if the population itself is not distributed normally. And in this case, this population was uniformly distributed because we had just worked with random numbers times a dollar multiple. So that's the central limit theorem in practice. The idea that the sample mean is normally distributed. So when we take a sample, we can have confidence based on the normal distribution that we're within a certain target range of the true mean. And remember the concept of an unbiased estimator, that the mean of the sampling distribution, in this case it's for 500, is going to be very close to the true population mean, and in fact it approaches exactly the same as the sample size gets large enough. Another thing in the book that I think would be very useful for us in understanding how this idea of the central limit theorem and how it works is this problem 714. I was really thinking about assigning this, but I decided it'd be too tedious, and it'll be much easier for me to show it to you. But what it says in the book in the problem is that we've got a file here that contains a very small population right here, only 5 members and their heights. And the purpose of this problem is to let you see exactly what a sampling distribution is. It says find the exact sampling distribution of the sample mean with size 3. So basically it says we're going to take every possible sample of 3 and we're going to do something called with replacement. So we're going to draw one, toss it back, and randomly draw another, toss it back, randomly draw another. So that what that indicates is that we could draw person 1 3 times, or we could draw person 5 3 times. We could draw person 1, 2, and 3. We could draw persons 3, 4, and 5, 2, 3, and 4. We draw person 1 twice and person 2, and so on and so on. And what we'll wind up with is 125 possible samples with replacement of size 3. And basically what the problem wanted you to do was list all of those. Okay, so we could have 1, 1, and 1, 1, 1, and 2, 1, 1, and 3, 1, 1, and 4, 1, 1, 5. Okay, then 1, 2, 1, 2, 3, 4, 5, 1, 3, 1, 2, 3, 4, 5, 1, 4, 1, 2, 3, 4, 5, 1, 5, 1, 2, 3, 4, 5, on and on and on. Then 2, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, on and on and on and on, all the way up to if we drew person 5 3 times. Okay, and we write down the heights, and that's done with VLOOKUP, and we then average them right here in column J. And so what we have here is all possible sample means. That's the full sampling distribution of this population. Now, the mean of the sampling distribution is going to be the average of the averages, if you will, the average of all the sample means we have here in our complete sampling distribution. So that's what's going on here. Notice that's just the average of column J entries. And then the standard deviation of the sampling distribution is the standard deviation of these sample means. Okay. And the exercise is really, it just says verify that equation 7.1 holds, that is that the mean of the sampling distribution is equal to the population mean. Well, over here we've calculated the population mean, average of these 5 numbers, it's 68.6, and look, that's the mean of the sampling distribution. Okay, so working this out, you verify that that fact is true. That's what we have back here. Okay, the mean of the sampling distribution, the expected value of the sampling distribution, is indeed the population mean. So that's what's going on right there. And then it says also verify that equation 7.2 holds, that is the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. Well, here's the population standard deviation, which is this, which is calculated on its own, divided by the square root of the sample size divided by the square root of 3. So that's sigma over square root of n. And that matches up our standard error calculation, or which is the standard deviation of the population. And that's verifying what we had here. Standard error, sigma over square root n. Okay, so our final piece for chapter 7 is going to be problem 7.7. It says a manufacturing company's quality control personnel have recorded the proportion of defective items for each of 500 monthly shipments of one of the computer components that the company produces. Here's the data. Quality Control Department Manager does not have sufficient time to review all of these data. Rather, she would like to examine the proportions of defective items for a sample of these shipments. For this problem, you can assume that the population is the data from the 500 shipments. So we've got the 500 entries here. So first off, it says in A, use Excel to generate a simple random sample of size 25 from the data. Okay, we know the drill here. We're going to create our random numbers, and then we're going to freeze them or fix them. So let's do that really quick, like fill that all the way down. Okay, copy them, paste the values, sort on them, sort on the fixed random numbers, smallest to largest will work. Okay, and I just realized these shipment numbers were formula reference. We could have copied and pasted the values there if I had known that, but I'll just move on because that doesn't really matter. Those are just arbitrary labels, basically. What we're interested in is these proportions, and we did indeed get those sorted when we ordered the random numbers. So let's just go ahead and grab the first 25 of them. That's going to be 2 through 26. Okay, Control C, and let's put these over here. So let's put that there, and let's label this n equals 25. And then we'll work our summary statistics over here. We want to, in part B, a point estimate of the population mean. X bar, of course, is our notation for the sample mean, and that is just the average of our sample, our 25 unit sample. And we get 0.55. It says, what is the sampling error? That is, by how much does the sample mean differ from the population mean? Well, let's put the population mean up here, and we'll label that, we'll just call that mu. And that's the average of B2 to B501.5. Okay, so the difference there, we just calculate that very easily. Mu minus X bar, and it's 0.5 less. Okay, now you might get a slightly different value for X bar, but we'll find that it's not going to exactly match the mu. So one of you might get really lucky and have it match the mu, but it's probably not going to match it exactly. Okay, and nor are we expecting it to. Okay, so that's B. C says calculate a good approximation for the standard error of the mean. The standard error of the mean is approximated by S over the square root of n. We still need to calculate X, so let's do that. Standard deviation of our sample, that's going to be equals standdev.s of the sample data, and that works out to 0.242. All right, so our approximation for the standard error of the mean is going to be that standard deviation of the sample divided by the square root of our sample size, which is 25. So there's our estimate of the standard error of the mean. Okay, now finally D says repeat parts B and C after generating a simple random sample size of 50. Okay, let's do n equals 50. My random numbers have regenerated a few times, so I'll just copy them and paste the values again in my fixed random number column. And then I'll again sort. I don't need to sort column A. In fact, I can just get rid of column A. It's just kind of junk right now. I'll sort on column C, fixed random numbers, smallest to largest again. And now I'm going to pick for our proportions, what we're measuring here, our defective proportion measurement. I'm going to take 50 now, the smallest 50 values. Control C, and put them over here. Okay, and I'm going to take the same. Yeah, I'm going to do everything I did in B. Control C. So my mu is still, that can be H1. My X bar is now an average of my larger sample. So I got 0.46. I went down to 50. I should have gone to 51 because the first row is a header. Nope, not that one. This one. That's not going to change my results very much, but it's important to be accurate. Yeah, I didn't change it at all. Standard deviation, standdev.s of that same range, which is L2 to L51. Okay, 0.286. My difference between the mu and my new x bar is 0.04. So I'm a little bit closer, which is what I would expect, but it's not necessarily the case. Let's calculate my standard error of the mean, and that's the same formula I used in C. That's my sigma here, or it's my S rather, not my sigma. It's my sample standard deviation divided by the square root of my sample size, which is now 50, remember. Okay, so my standard error is quite a bit smaller. It's 0.040 and it was 0.048. So I did decrease my standard error, I'd say substantially. And it says in the final part of the question, is the standard error bound to be smaller than the one in part C? Well, we're dividing by a larger number here, so the answer of course is yes. And the lesson is that with the larger the sample size we have, the smaller the standard error. Typically, also, the closer our x bar is going to be to the mu, you might not have gotten that result, and I wouldn't necessarily expect that, but typically with the larger sample, our x bar is also going to be closer to mu. But the important thing is that our standard error is lower. And what does that mean? What does that mean? Well, let me jump back to this histogram, this normal distribution of our sampling distribution. This histogram of our sampling distribution again. If our standard error is lower, that's the standard deviation here, remember. So that means we're getting a tighter and tighter distribution of our sample mean. So we're getting a better and better chance that we're right on the center point of that. And remember, the center point of that is the population mean because it's an unbiased estimator. That's what we just proved when we worked out 714 right here. Okay, remember, the population mean is the mean of the sampling distribution. Okay, so that is what we need from Chapter 7. I hope you understand it. I hope you can work through a problem on your own. And I will sign off now, and in a couple of days I'll see you again, and we'll start working through Chapter 8.